Hello everybody. Thank you for staying till the late evening, let's say, the late afternoon. And so I'm Riccardo Giampiccolo, and I'm a postdoc researcher at the Image and Sound Processing Lab here at the Politecnico di Milano. And today I'll try to sum up my research that I did during my PhD, titled Multiphysics Modeling of Audio Systems in the Wave Digital Domain. And first of all, I would like to thank the Dimitri Chorafas Foundation for this award. I'm very honored to receive it, and would like to thank my supervisors, Professor Augusto Sarti and Alberto Bernardini, and even the company that sponsored and funded my PhD, that is Inventum Semiconductor. Audio systems are complex multiphysics systems whose physical domains are not only affected by many nonlinearities, but they do interact in a nonlinear fashion. And what we wanted to do was actually to derive digital signal processing techniques, or at least to lay the foundation for deriving digital signal processing techniques able to linearize, compensate, and virtualize these audio systems, but leveraging the physics of the device. And in order to do that, so multiphysics models, accurate and lightweight multiphysics models, must be derived. So, as I said, the aim is to have multiphysics modeling for digital signal processing, and we divided the work into 3 parts. So we have a first part related to circuital modeling, in which we derive models of audio systems. Then we derive methods for the efficient simulations of these systems, and then finally we combined models and methods together in order to provide digital signal processing techniques. So let's start with the first part, about circuital modeling, and we focused our interest on those systems characterized by an input, an output, or both variables belonging to the electrical domain, and has been demonstrated that lumped element models are very effective in modeling such systems, and lumped element models can be described by means of circuits. So we actually were interested into finding ways of simulating circuits in a very efficient fashion. And there are many techniques available on the literature. Most of them consider the circuit as a whole and apply global discretization methods and approaches. For example, the modified nodal analysis that is at the basis of SPICE and other methods. But when we have multiple nonlinearities and when we want to use implicit discretization methods, typically we end up with systems of implicit equations, and thus the most widespread solution is to use multivariate iterative solvers in order to find the actual solution of the circuit. But if the circuit is big, or if we have complex nonlinearities, of course, this is a demanding operation, and it costs. And thus, what we wanted to do is to find an alternative approach that allowed us to have cheaper and more efficient methodologies. And we actually took into account wave digital filters. So wave digital filters were theorized by Fatwise in the 70s for the digital implementation of passive analog filters. And they start from a portwise description of the reference analog circuit, and we substitute, so we have a domain shift, we substitute voltages and currents with an incident wave A, a reflected wave B, and with the introduction of a free parameter per port that is called a port resistance. So, of course, from the 70s till now, a lot of theory, a lot of advancements in such a theory have been provided, till the point that now we are able to model nonlinear circuits, nonlinear systems in a very efficient fashion. This is actually the framework that we selected, that we used throughout the research for providing, at the end, even digital signal processing algorithms. So as far as models of audio systems, I will fly over it. I will just mention some of them. So we took into account piezoelectric loudspeakers, and we provided efficient and explicit models for such loudspeakers, considering quasi-static regime and even operation outside the quasi-static regime. We took into account guitar pickups, and we provide nonlinear circuit in order to take into account the nonlinearity introduced by the magnetic poles inside of it. But I would like to concentrate a little bit more on audio transformers, because audio transformers are actually very important for recreating the sound of loudspeakers and amplifiers, as they contribute to this sound. And this is a typical output stage of a vacuum tube guitar amplifier. And what we wanted to do is to find a methodology to actually model, to be able to model the nonlinearities affecting the magnetic domain. And what we did is actually to take into account magnetic equivalent circuits, so the analogy between voltage and magnetic-motive force, and between current and magnetic flux, in order to provide a multiphysics circuit able to describe even the nonlinear, both the nonlinearities in the electrical and the magnetic domains. So, for example, we may consider the core, the magnetic core, as an EI core, which can be described in the magnetic domain by means of that equivalent circuit, where resistances here are reluctances, and we have that windings can be represented by means, can be turned into magnetic-motive force sources, following the convention that is reported on the right. And by means of this modeling, we are able to take into account the nonlinear characteristic of magnetic cores, and to model them together with the electrical ones. We took into account two nonlinear phenomena, core saturation. There were models in the literature of audio systems, of audio signal processing, that were actually too simple to describe real curves like this, that has very sharp knees. So we proposed to use canonical piecewise linear functions in order to represent the curve, so a nonlinear characteristic in the magnetic domain. In particular, this is a nice model because it can be tuned in a data-driven fashion, selecting points on the curves. So, for example, if we select those 8 points on the curve, we are able then to tune the model and to have a very efficient and global representation of the nonlinearity. And then we took into account even hysteresis. So hysteresis are much complex phenomenon, and thus we believe that here the power of neural network and of neural networks actually comes out. So we, in fact, if we want to describe rate-dependent hysteresis, which is a phenomenon that hysteresis that changes according to the rate of the input, we know that the analytical models cannot do that in a very good fashion, or at least they are very, very expensive. And so we actually used a recurrent neural network, a Price-Ank recurrent neural network in this case, that was able to actually capture that, that phenomenon. And we trained the neural network directly in the wave digital domain. So, for example, if we have an output stage of a vacuum tube guitar amplifier, and in this case we think the transformer to be characterized by that magnetic core, so a loop, because in this case we are able to represent it by means of a single reluctance, which is the one that will be affected by hysteresis. So if we do that and we create the multiphysics circuits, then we can train that reluctance on the data set, which is that on the right, and we can do that directly in the wave digital domain, and we can encompass that nonlinearity into a weight digital block. And this was probably the first attempt in the literature to do so, to merge neural networks and weight digital filters together. So we have models of audio systems, but we want to find and propose methods to actually simulate those models in an efficient fashion. So we took into account different strategies. For example, here is the method that we call a hierarchical scatter iterative method, which is an iterative method that we proposed for solving circuits, multiphysics circuits. So multiphysics circuits characterized by many junctions and elements. We can organize the junctions, the elements, and so on in a connection tree where we have a root, which is the red circle, then we have the topological junctions that are the black nodes, and then finally we have the leaves that are the white nodes. So we have iterative procedure. First of all, we compute the waves reflected from the leaves, then we propagate this information. So we compute the waves reflected from the nodes till we reach the top, where we have the roots. We compute the waves reflected from the root, and then we propagate everything down. So we compute this till we reach convergence. And by means of this method, we were able actually to model, to simulate the model that I presented before. So we have our output stage of a vacuum tube guitar amplifier. We have the magnetic the transformer that is represented by this magnetic circuit. This is the multiphysics circuit that merges both electrical and magnetic domain together. And this is the wave digital filter implementing this circuit. So at the end, we have 6 nonlinearities in the magnetic domain with this characteristic. This is just the first quadrant. And these are some results. So we were able to get the same accuracy of other simulators, like Math-Werstin's case, but we were able to do that in a more efficient fashion. So, so just to give an example, not with this circuit, but with a more complicated one, with Simscape, we simulated that in 2 minutes instead with this method with tens of seconds. And the nice thing about this method is that a lot of operations are embarrassingly parallelizable, which means that we can solve them independently of the others, and thus we try to merge some very simple concept borrowed from the parallel computing theory in order to speed up the simulation. So for example, we computed the parallelism of this structure, and we found out that we could use two threads in order to solve this wave digital filter. So we divided the solution of the threads in the iterative procedure, the solution of the wave digital blocks in the iterative procedure among these 2 threads. And at the end, we found out that we were able actually to get 30% of speed up with respect to the serial structure. So we have seen some models, we have seen some methods for the efficient simulation of those models and audio systems in general. What we want to do is actually to use both to propose some signal processing algorithms. In particular, our aim is to improve the acoustic performance of audio systems. And so, for example, let us imagine this scenario. So we have an audio actuator, and like a loudspeaker, we know that it produces some distortion. So we would like to add a precompensation algorithm that is able actually to drive the actuator in order to get a well-equalized, let's say, sound signal. And we can have the dual chain for sensors as well. So we want to acquire a very, let's say, good signal out of sensors. And we base our approach on circuital inversion, in particular on the theorems that are based on nullers, because we want to leverage all the physical modeling that we have done in order to actually propose processing chains. And nullers are theoretical two-part elements that are composed of other 2 theoretical elements. We have an annullator represented by means of an ellipse, that has 0 voltage and current, and then we have a narrator represented by 2 circuits that has unconstrained voltage and current. So by means of this element, we're actually able to revise Liuchik's theorem of inversion that says that if we have a nonlinear network that has an nullor inside, if we name the input U and the output Y, we are actually able to get the exact inverse by swapping the position of the input generator with the output, by driving the inverse with the output of the direct system, and by reading the input on the input port. So by means of this circle, we are actually able to obtain the exact inverse of a physical model, even if it is, of course, multiphysics and characterized by many nonlinearities. So we actually propose the task of what we define the task of virtualization, that is to digitally alter the acoustic behavior of an audio sensor or actuator with the aim of mimicking that of a target transducer. In fact, we can have a chain for virtualization of actuators. So we have a physical direct system that is at the end of this chain, and then we want to impose a target behavior, which may be, for example, the linearized version of that physical model, or other behaviors like another physical systems, for example. So we have the 2 blocks in the digital domain. So if we tune the inverse system to be the actual inverse of the physical system, in an ideal processing, those 2 blocks cancel out, and thus what remains is just the target behavior. And we can have this the dual chain even for sensors. And I have a very brief example for you. So we have the model of a guitar pickup, and we can derive the inverse. So it's very, very simple to do that. We actually exploit most of the circuit that we already have. Then we can implement everything into the wave digital domain. And what we can actually do is to propose some sort of processing. So here we have 3 different pickups. We know that those are actually characterized by different spectra. So it is interesting to change the pickup if we want to give different coloration to sound. So imagine to have recorded an electric guitar, and then you wanted to want to change the pickup that you used for recording that sound in post-processing. With this methodology, you can. And in fact, this is what we did. So we consider as an input signal the displacement that we obtain by considering a plucked string simulated through the Karpelus-Strong algorithm. And then what you see is that we were able to turn the SSL5 pickup into an SH to N pickup, because the orange is the starting point, the red is what we wanted to achieve, and then by means of this processing chain, we were able to get the blue curve that is actually overlapped to the target one. So there are cases in which these processing chains, so these virtualization chains, cannot actually work, because we have 2 strict physical limitations of the devices. It is the case, for example, of small size loudspeakers. So small size loudspeakers have a very high cutoff frequency, and for musical purposes, this is actually a problem, because we do not reproduce bass frequencies in a pleasant fashion. And of course, direct bass boosting is not a solution, because we can damage the transducer, or we can even create more distortion. Thus, what we propose to do is to actually exploit some psychoacoustics effect, like that of the missing fundamental. In fact, the brain can perceive a tone, not only if it is really present in the audio track, but also thanks to the periodicity of its higher harmonics. So we actually presented different methods. This is a typical time domain block scheme, we have a crossover network that separates the low end and the high end. Then we process just the low end by means of a nonlinear device in order to have harmonic generation, and then we have a summing stage. The problem with this diagram is that the crossover network actually generates intermodulation distortion, and so we propose to substitute the crossover network with a music demixing model, which is a deep learning model that basically extracts stems out of music signals, which means we can extract just the bass track, just the guitar track, and so on by means of this model. So we propose this pipeline. It is actually the subject of a patent that we filed to the European Patent Office and the American Patent Office. And so we have a music demixing model that extracts just what we want to process. For example, the bass, because we want to process just bass frequency, so we have the bass or the low end of the drums or the low end, I don't know, of the piano track and so on. And then we apply the processing only on those stems. So we add some normalization, some nonlinear functions and so on in order to trigger the missing fundamental phenomenon. So at the end, of course, we organized a perceptual test, and these are the results. So we asked the listeners to rate both the basic audio quality and the bass enhancement, and we see that our method, that is the one in red, is actually the one that is performing better in both the two tests against other methods of the state of the art. So some conclusions. So we propose multiphysics models of audio systems, and then we propose methods for the efficient emulation of those audio systems, of those nonlinear systems, and then we try to merge models and methods in order to provide virtualization chains in order to actually improve the acoustic performance of audio systems. And then when these algorithms are not able actually to reach our goal due to physical limitations, we propose to go for psychoacoustics based algorithms. So this is a list of the publications that I was able to publish during the PhD. And so that's all, and I thank you all for the attention.